We have confirmed more than 5,000 planets beyond our solar system, yet we have never actually seen a single one with our own eyes. Even the most powerful telescope ever built, the James Webb Space Telescope, does not capture direct images of these distant worlds, it only collects data. So if we have never truly seen them, how can we be so certain they exist at all? The answer to that question reveals a truth about how we observe the universe that completely redefines what the word see actually means. We are taught to trust our eyes. We say seeing is believing, and we imagine astronomers spend their nights peering through giant telescopes at swirling, colorful planets. The reality is far stranger and far less visual. Even with our most powerful instruments, we have never once laid eyes on an exoplanet. We have confirmed more than 5,000 of them, yet not a single one has ever appeared as a dot of light in an eyepiece. The planets are simply too small and too dim next to the blinding glare of their host star. According to NASA's Exoplanet Exploration Program in 2023, direct imaging works only for a rare few, giant young planets that orbit at a great distance from their star, where their faint infrared glow can be separated from the stellar light. For the overwhelming majority, the planet is utterly invisible. So how do we know it is there? We know a planet exists the way we know the wind exists. You do not see the wind itself. You see the leaves trembling, the dust swirling, the branches bending. The wind is an invisible force, and you infer its presence from its effects on things you can actually see. This is precisely how we see nearly every exoplanet. We watch the star. We measure its light, its motion, its color. When a planet tugs on its star, the star wobbles. When a planet passes in front, the star dims. These are the leaves shaking. The planet itself remains hidden in the dark. The only exception came in 2022, when the James Webb Space Telescope captured the first direct image of an exoplanet, a hot gas giant called HIP 6542T6b, a world 6 to 12 times the mass of Jupiter sitting 385 light-years away. That image was a triumph, but it was also a warning. It worked only because this planet is huge, young, and orbits far from its star. It is the rare tree that lets you see the wind. For everything else, we are blind. This is the great secret of modern astronomy. When scientists announce a new discovery, they are not sharing a photograph. They are sharing a story pieced together from numbers, from graphs, from the subtle flickering of a distant sun. Seeing in science does not mean with your eyes, it means measuring, calculating, and inferring. It means trusting that the universe follows laws we can understand, even when those laws show us things we cannot directly observe. The data is the vision, the math is the telescope. And this indirect way of seeing has revealed thousands of worlds, each one a ghost we have learned to know intimately. But if we are not looking through a lens, what exactly are we looking at? What tool is so precise that it can detect the presence of a planet that has never been seen, a world lost in the glare of its own sun? The answer begins with a discovery that shocked the world in 1995, and its name sounds more like a detective story than a scientific instrument. In November 1995, Swiss astronomer Michel Mayor and his graduate student Didier Queloz were at the Haute-Provence Observatory in southern France, staring at a star named 51 Pegasi. They had no image of a planet, no glowing dot in a telescope eyepiece, just a subtle wobble in the star's spectrum of light. That wobble was the telltale sign of an invisible companion, a giant world yanking its sun back and forth with its gravitational pull. This discovery, recognized by the Nobel Prize in 2019, didn't just find a planet. It flipped our understanding of solar systems upside down. The planet, 51 Pegasi b, was a colossal gas giant, but it orbited its star in just a few days, a frenzied sprint compared to Jupiter's leisurely 11.86-year journey around our sun. It's a hot Jupiter, a class of world that we never even imagined could exist, locked in a scorching, tight embrace with its parent star. So, how do you catch a wobble that small, and what does it really tell us about the invisible world causing it? The answer is the pulse of the star itself, and it relies on a technique called radial velocity. Think of a star and its planet not as a fixed center and a circling satellite, but as two dancers holding hands, spinning around a shared point. Even a small planet gives a mighty tug, making the star itself move in a tiny circle. As the star moves toward us, its light waves get compressed, shifting toward the blue end of the spectrum, and as it moves away, they stretch, shifting toward the red. By measuring this back-and-forth shift, we can feel the planet's influence, no image required. It's a startlingly clever trick, a way to listen to the cosmos rather than see it, and its success is staggering. The radial velocity method has been responsible for confirming over 1,000 exoplanets with this exact technique, a powerful instrument built on a cosmic dance. You can't see the planet, but you become certain it's there because of the rhythm of the star's light, a tiny, rhythmic hymn to a world hidden in the dark. So, if radial velocity is like listening for a whisper, what if there was a way to actually glimpse the shadow of the planet itself, to catch it as it passed across the face of its sun? We have never actually seen an exoplanet when we claim to discover one, and that distinction becomes clearest with the most successful method of all. The transit method works by watching a star's light dim ever so slightly as a planet passes directly in front of it, a tiny eclipse that blocks a fraction of a percent of the star's brightness. This approach has been so effective that it has confirmed more than 3,900 exoplanets according to the NASA Exoplanet Archive as of 2024, far more than any other technique. So how does one machine turn this faint flicker into a map of thousands of hidden worlds? In March 2009, the Kepler Space Telescope launched with a single audacious mission to find planets like ours. For 9 years, it stared unblinkingly at one fixed patch of sky in the constellation Cygnus, recording the brightness of more than 150,000 stars simultaneously, as noted by NASA in 2018. It watched for the telltale dip of a transiting world, and during its lifetime it found over 2,600 confirmed planets, at one point accounting for more than half of all known exoplanets. The sheer scale of that achievement didn't just expand our catalogue, it revealed that planets are not rare exceptions but a ubiquitous feature of the galaxy. But wait, this is where the true wonder of the method clicks into place. While the transit tells us a planet exists and how big it is, it does not hand us a picture of the planet itself, only the shadow it casts. You can see this for yourself by visiting NASA's Exoplanet Archive at exoplanetarchive.latech.edu and using the Confirmed Planets search tool to pull up the raw data on any of these distant worlds. Yet knowing a planet is just the opening note, because we now stand at the threshold of wanting more than mere existence. We want to know what lies hidden in that planet's atmosphere, and that is the next great leap in our cosmic sight. We've learned where planets hide, but now we enter the more intimate act of reading what they're made of. When a planet passes in front of its star, a sliver of starlight filters through the planet's atmosphere, carrying its chemical secrets. Scientists have mapped these faraway skies using a technique called transmission spectroscopy, patiently splitting that filtered light into its component colors. Each missing wavelength is a fingerprint, a clue that some molecule like water vapor or sodium is absorbing that exact shade. The James Webb Space Telescope scored a historic win here in August 2022 by detecting carbon dioxide in the atmosphere of a planet called WASP-39b, the first time this molecule was confirmed around an exoplanet. It's a feat of interpretation that transforms an invisible world into a list of ingredients we can study. Even color becomes a scientific datum, since a planet like HD WASP-733b shines a deep blue that has nothing to do with oceans, but instead signals a scorching atmosphere where glass rains sideways. Now pause for a moment and think about the images of these planets you've seen splashed across news sites. Swirling blues and fiery oranges. Almost all of them are pure illustration, not photographs, since our telescopes are measuring light, not capturing portraits. So the next time you look at a headline about a distant world, remember that every dramatic picture is a careful guess built from real data, and the real magic is happening in the numbers. With all these tools at our disposal, what are the greatest records we've broken so far? Before 1992, humanity had never confirmed a single planet beyond our solar system, a remarkable blind spot that stretched across the entire history of astronomy. That silence was broken when scientists detected two worlds orbiting a pulsar known as PSR B1257+12, a dead, flashing stellar remnant that seemed like the least likely place to find planets. The discovery, announced in the journal Science that year, proved that planetary systems could exist in the most extreme environments imaginable. It was the first crack in the assumption that our solar system was the blueprint. But even then, no one had actually seen one of these distant worlds with their own eyes. That changed in 2004 when the Very Large Telescope in Chile captured the first direct image of an exoplanet, a giant named 2M1207b, a blazing gas world about 5 times the mass of Jupiter. For the first time, there was a photograph, not just a data point, of a planet orbiting another star. Can you feel the shift in what seemed possible? The pace only accelerated, and by March 2022, the confirmed count of exoplanets crossed a monumental threshold. NASA celebrated the milestone with a striking visualization, placing each of the 5,000 known worlds in their positions within the Milky Way, a glittering map of our growing knowledge. And the numbers keep climbing. As of April 2024, NASA's Exoplanet Archive lists 5,609 confirmed planets, with more than 10,000 additional candidates waiting for their moment of verification. Yet, behind every one of these milestones, from a wobbling pulsar to a direct snapshot, lies that humbling truth. We are decoding the universe with shadows and whispers. So, if all this began with a few bizarre worlds around a stellar corpse, what does that say about the solar system we call home? You look at our solar system and you see a neat arrangement: small rocky planets near the sun, giant gas planets further out. That tidy picture becomes the template in your mind for what a planetary system should look like. But the data from the Kepler telescope tells a very different story. And that story begins with a class of world we do not have at all. Super-Earths. Rocky planets larger than our own but smaller than Neptune are the most common type of planet we have found in the galaxy. They are everywhere, and yet none of them orbits our sun. Why is the most typical planet in the Milky Way completely absent from our cosmic neighborhood? The extremes only make the strangeness deeper. Consider K2-137b, a planet so close to its star that it completes an entire orbit in just 4 hours. Think about that. A full year on that world lasts shorter than a single school day. Earth needs 365 days to circle the sun, and that difference is not just a number. It reveals how wildly different the architectures of other systems can be. Density, too, becomes a concept that stretches beyond what our local worlds can teach us. There is a planet called WASP-17b that is so puffy, so low in density, that it is about 10 times lighter than water. Nothing in our solar system even comes close to that kind of physical makeup. And it was discovered only because the transit method caught its bloated silhouette crossing its star. Some planets do not even have the privilege of a quiet, single star. 30 Arietis, for example, is part of a system where the sky holds multiple suns, a world caught in a gravitational dance far more chaotic than anything we experience. And then there are the loners. Rogue planets, the ones that drift through interstellar space without any star to call home, might actually outnumber the planets that stay bound to their suns. Our solar system orbits one star, but the universe seems to favor worlds that wander alone or huddle in crowded, strange systems. So if our arrangement feels normal, maybe it is the exception. How can we be certain that what we see out there is even real? So how do astronomers actually confirm that a distant world is a planet? The answer is rooted in a level of statistical rigor that might surprise you. A confirmation demands more than a single promising blip. It typically requires a statistical probability greater than 99% that the signal isn't noise, a standard detailed in a 2017 paper in the Astrophysical Journal. This is because the universe is messy, and the search for planets is riddled with cosmic illusions. In fact, scientists have found that up to 70% of observed transit signals actually contamination or caused by other phenomena, like a binary star system, that must be filtered through rigorous checks before being accepted as a true planet. To overcome this, patience is a core scientific tool. The process of confirming a transit often requires observing at least 2 identical dips in starlight, which means waiting for the planet to complete a full orbit around its star. And to really understand a world, you must combine different types of observations. Transit data reveals a planet's diameter, while the radial velocity method provides its mass, and together they unlock its density and likely composition. If you want to see this for yourself, you could go to the official archives and pick any confirmed planet, checking its mass, radius, and orbital period. Science isn't a leap of faith, it's a slow, deliberate, and incredibly careful process of building a picture. So, with this level of scrutiny, what kind of future are we building to see these distant worlds? The James Webb Space Telescope, a $10 billion marvel launched to peer into the infrared universe, represents our most ambitious leap yet in the art of seeing. It is engineered to cut through the cosmic dust that blinds other instruments and to dissect the very atmospheres of distant worlds. With this power, Webb is now turning its gaze toward rocky planets like TRAPPIST-1e, a world orbiting a red dwarf star a mere 40 light-years away, hunting for the chemical whispers of a potentially life-bearing sky. Beyond the hardware, the future of this field is also being written in lines of code, as scientists deploy machine learning to sift through the colossal archives of data from the Kepler mission. These algorithms are proving remarkably adept at flagging the faintest transit signals, the tiny periodic dips in starlight that might otherwise slip past a human observer. And once a planet's basic properties are locked down, researchers are taking the next step, building sophisticated 3-dimensional climate models to simulate the raging winds and swirling clouds on these alien spheres. The guidance for you is simple. Begin with the jarring statement that we have found thousands of planets yet have never seen one, and let that curiosity be your lead. So, if we can map the weather of a world trillions of miles away, what other seemingly invisible truths are waiting for us to finally observe? In 2016, a telescope perched in the Chilean mountains spotted something that would shake the foundations of planetary science. The TRAPPIST telescope, peering at a dim red star just 39.5 light-years away, found a system unlike anything we had ever seen. It wasn't a single planet that caused the stir, but an entire family of them, 7 rocky worlds huddled close to their tiny sun. 3 of those worlds, we quickly learned, were sitting right in the habitable zone. Was this the cosmic jackpot we had been waiting for? The system defied every expectation we had built from our own solar neighborhood. All 7 of these planets are roughly Earth-sized, their orbits packed so tightly together that they would fit within the distance from the Sun to Mercury. This arrangement is wildly different from the vast empty space that separates our own planets, and it points to a formation history we are only beginning to understand. Here, in a single compact system, we have a complete menagerie of worlds that all share a similar rocky composition. The engine driving this entire dance is a star that seems almost impossibly faint. TRAPPIST-1 holds only about 8% of the Sun's mass, making it a dim red dwarf with a fraction of our star's luminosity and temperature. Because this stellar furnace is so weak, its planets have to orbit at a breathless, crushing distance to stay warm enough for liquid water to exist. Imagine those worlds, their skies glowing with a perpetual dim cherry-red light, a far cry from our brilliant yellow days. This discovery didn't happen in a vacuum, as it built on a principle we were just starting to grasp. The earlier finding of Proxima Centauri b, a planet around another dim red dwarf, proved that these small stars could be planetary hosts after all. But it's the detailed structure of TRAPPIST-1 that shows us that the habitable zone for such a star is a very crowded, very tight place. The silence in the dark of that system is not empty. It is practically packed with potential. But here is the question that pulls at every astronomer who looks at that data. A question that bridges the gap between discovery and understanding. If this system is so far away, how can we know what is actually happening on those distant, rocky surfaces? There is a strange humility in realizing that most of what we know about distant worlds comes not from a direct glimpse, but from a patient study of their shadows and their tugs. Consider the discovery of Proxima d in 2022, a third planet in the Proxima Centauri system with only a quarter of Earth's mass, found through the subtle data of the Very Large Telescope. It is a quiet reminder that our instruments can perceive what our eyes cannot, revealing worlds that are fragile and faint. Yet, even this faintness is a form of information, a whisper that we have learned to amplify into understanding. Some of these whispers carry the signature of water, as seen with K2-18b, where the Hubble telescope first detected water vapor in its atmosphere back in 2019, opening a new door to questions of habitability. The mere presence of that molecule transforms a distant point of light into a potential haven, a place where the chemistry of life as we know it might begin. We are not just counting objects anymore. We are searching for ingredients, looking for the familiar in the vastly unfamiliar. This search is inherently biased, however, by the limits of our own perception. The vast majority of confirmed exoplanets are those with radii between 1 and 2 times that of Earth, simply because anything smaller is too difficult to spot with current technology, the signal being far too weak against the glare of the host star. Similarly, most of these discoveries lie within a few hundred to a few thousand light-years from us, although some have been found at distances exceeding 25,000 light-years. Our catalogue of worlds is a reflection of our observational power, a map that shows not only what is out there, but also the boundaries of our current sight. What is truly staggering is the estimate that more than half of all Sun-like stars in the Milky Way host at least one planet, a conclusion drawn from the Kepler mission's data. This single statistic transforms the universe from a seemingly empty void into a crowded arena, a place teeming with potential. With so many stars and so many planets in orbit around them, the notion of being unique becomes almost statistically implausible. Could it be that we are just beginning to learn how to see? We have spent this entire journey describing planets we cannot touch, measure, and infer. Yet even with the remarkable methods of transit and radial velocity, there are still more ways to listen to the cosmos, each one pushing the boundary of what we can detect. Gravitational microlensing, for instance, has already uncovered more than 200 exoplanets, some located tens of thousands of light-years away, much farther than most other techniques can reach, according to the NASA Exoplanet Archive in 2024. This method relies on the gravity of a foreground star to bend and magnify the light of a background star, acting like a natural lens that reveals a hidden world. Then there is the subtle art of timing, where scientists measure minute changes in the pulses of a pulsar, a technique so precise it can uncover planets smaller than Earth itself, as noted by NASA Exoplanet Exploration. When we combine these methods with the ones we have already covered, a pattern emerges. Our vision is not limited to the literal act of seeing, but is defined by our capacity to gather and interpret data. This realization becomes crucial when we look at the images of these far-off worlds, because what we are actually looking at is rarely a photograph. The breathtaking portraits of glowing gas giants and rocky super-Earths we see online are often artistic impressions, detailed illustrations based on real data but fleshed out by imagination. To tell the difference, you should look for the phrase artistic impression or a similar caption within the image's description, a simple but essential step recommended by NASA and scientific publications. Once you spot that label, you can then cross-reference the illustration's details with the actual measurements on the NASA Exoplanet Archive, which lists the planet's true mass, radius, and orbital period. This allows you to see which parts of the picture are grounded in hard numbers and which parts are the artist's creative interpretation of that data. The contrast between the uncertainty of a painting and the precision of the underlying numbers is a lesson in itself, teaching us to appreciate the artistry of science communication while understanding its limits. What emerges from this complexity is a profound truth. Our scientific sight is a layered and collaborative process, one that pieces together many different signals into a coherent picture. The radial velocity method gives us a planet's mass, the transit method reveals its size, and spectroscopy unveils the gases in its sky, each technique a different sense contributing to our understanding. A transit observation might tell us a world is wide, but it is the radial velocity measurement that tells us if it is heavy, and together they reveal its density, which hints at whether it is made of rock, gas, or ice. Lensing catches the faint glimmers of distant worlds that would otherwise remain invisible, while timing catches the faint tugs of small companions that other methods might miss. It is this combination, this constant cross-referencing of independent signals, that transforms isolated observations into a confident, three-dimensional model of a place we will never physically visit. The beauty is not in the single measurement, but in the elegant way the universe's coherence allows these different tools to agree with one another. So what is the final takeaway from all this? We have mapped a cosmos teeming with planets, from the scorched ultra-short period worlds to the free-floating nomads drifting in the dark, all without ever laying our eyes on a single one of them directly. Our concept of seeing has been permanently expanded, no longer confined to the light that happens to hit our retinas, but encompassing the entire process of detection, measurement, and inference. This journey of discovery is not a simple act of observation, but a demanding process of hypothesis, confirmation, and refinement, all building towards understanding our place in this vast and crowded galaxy. And the most profound question is not just whether these planets exist, but whether our incredible indirect way of seeing them is the very tool that will reveal we are not alone in the universe. We began with a strange confession. We have confirmed more than 5,000 worlds, yet we have never truly seen a single one. Every method we explored, from the wobble of a star to the shadow of a transit, is a way of reading what our eyes cannot capture. We know these planets exist because their gravity tugs, their darkness dims, and their atmospheres paint fingerprints across a spectrum of starlight. This is the quiet power of science, the ability to know something is there without ever laying eyes on it. Theoretical models from NASA in 2013 suggest there could be around 21 billion Earth-like planets in our galaxy alone, each one sitting within its star's habitable zone. Think of that number for a moment, a figure so vast it dwarfs every grain of sand on every beach we have ever walked. And we are not just counting distant possibilities, we are already focusing on specific candidates like LHS 1140b, a planet orbiting a red dwarf star that stands as one of our best hopes for studying alien life. With a radius about 1.7 times that of Earth and a mass pushing 6.98 times ours, it is a rocky world we might one day understand in intimate detail. So we have never seen a planet with our own eyes, and yet we know they are there, we know what they are made of, and we know which ones might hold oceans. That is not a contradiction, that is a triumph. It is a reminder that our vision is not limited to our biology, but is expanded by our imagination and our relentless curiosity. The journey to understand these distant worlds is a testament to what we can achieve when we refuse to accept the limits of our own senses. Now the only thing left to do is to ask your own question, to follow your own thread of curiosity into the dark. Start with a single what if and see where the data leads you, because that is where every great discovery begins. And when you look up at the night sky, remember that the stars are not just points of light. They are homes to worlds we have yet to meet. If there is another planet out there, looking back at us through its own instruments, do you think they are asking the same question about us?